Welcome to another Math Rescue video. I'm Victoria, and today we're going to talk about limits. Limits are usually the first topic covered in a calculus course. I know I'm skipping pretty far ahead, considering my last video was an algebra topic, but I really want to get into higher math now, and calculus is the best place to start. In these calculus videos, I'm going to assume that you know algebra and trig, so I may skip some basic steps in order to show more complicated steps. If you need clarification, you can ask in the comments section or send me a message. Limits are the foundation for most of the higher math, and especially derivatives, which come next. Most students struggle most with the basic definition of a limit, so I'm going to try to explain the best I can. The accepted formal definition is given here. The limit of a function is a value L if we can make the values of f of x arbitrarily close to L, as close as we wish, by taking x to be sufficiently close to a on either side of a, but not equal to a. I know, that sounds incredibly complicated. It will make much more sense when we look at various notations and a few examples. Here are two ways we commonly represent limits. The first is most common, and it is said, the limit of f of x as x approaches a equals L. Another way of saying this is f of x approaches L as x approaches a, written as you see at the bottom. This notation might make more sense to you. We are finding the value that limits the functional value as x approaches some number a. You may have seen this notation in your algebra class if you studied end behavior and vertical asymptotes. In the beginning, you will estimate limits using a table of values. Let's look at an example. Estimate the value of the given limit by using a table of values. The function we are considering here is x minus 1 over x squared minus 1, and we are interested in the limit as x approaches 1. Notice here that the functional value precisely at 1 is undefined, but this does not mean there isn't a limit here, as you will see in a moment. It is easier to visualize this if you set up two tables of values, one for x values less than the number under consideration, and one for x values greater than the number. Here we are considering the number 1. You need to choose about 5 numbers for each table, being sure that the numbers gradually become very close to the number in question. Notice the last number I chose on the left, 0.9999, is very close to 1, but is still less than 1. On the right, my final number is 1.0001, which is also very close to 1, but is on the right side of 1. Can you see a pattern in the functional values as the x values approach 1? You should notice that the functional values are approaching 0.5. This is evidence that the limit here is probably 0.5. Look at the graph of this function on the calculator on the left. When I first graph it, everything seems normal. But when I ask the calculator for the y value at x equals 1, it cannot give me 1 because f of 1 is undefined. Technically, there is a hole in the graph at x equals 1, which cannot be seen on the calculator. Using a calculator to obtain a table of values is sufficient in the beginning for finding some limits, but quickly becomes deficient because a calculator only estimates values and cannot always determine small changes in functional value. Later we will learn how to accurately determine a limit. Sometimes the limit on the right side of a value is different than the limit on the left. This is verbalized as a one-sided limit. We change the notation by including a superscript on the a value, indicating whether we are taking the limit on the left, which is a minus sign, or on the right, which is a positive sign. When we say the limit, we specify which side we are approaching a from. This theorem tells us that a limit only exists if the right and left-handed limits are equal. Notice the use of the double-sided arrow in this theorem, which is symbolic of the phrase if and only if. Visualize this as the statement working in both directions. If the limit as x approaches a equals L, then it must be true that both handed limits are equal to L. Also, if both handed limits are equal to L, then it must be true that the limit as x approaches a also equals L. If these limits are not the same, then the limit at that value does not exist, and we write that as dne. In our example of finding a limit using a table of values, the tables showed that as x approached 1 from either side of 1, the limit value was still 0.5. In the next video, we will talk a little more about limits and how to find precise values for them instead of using a calculator to estimate. Follow the link in the description to my blog post introducing limits, where you will find another example and more discussion than I could fit in this video. If you like this video or found it helpful, please subscribe to my channel to see more videos like this one. If you have any questions about this topic or suggestions for future topics, please leave a comment below the video.